Okay, shall we, Professor Zhou?
Okay, yeah, I'm ready.
Yeah. Let me give a very brief introduction. Okay, welcome all to this one-word seminar on machine learning. And today we are very happy to have Professor Difan Zhou from Hong Kong University. So, Dr. Zhou is an assistant professor in computer science department, an institute of data science at HKU since 2022. He has received his PhD in Department of Computer Science from University of California, Los Angeles. His research interests are broadly in machine learning, deep learning theory, graph learning, and interdisciplinary research between AI and other subjects. His research is published in top machine learning conferences and journal papers. He served as area chair, senior chair in many top conferences. So today we are very happy to have Professor Zhou. Now all is yours.
Okay, so first, thank you very much. Thank you, Professor Xu, for the introduction, and thank everybody for joining my talk. So, the title of my talk is the implicit bias of learning separable data, and we want to focus on the role of optimization algorithm and the model architecture. So, this is a joint work with Chen Yang, Yuan, Chunchun, and Yuanzhi. Okay, let's start. So first, let me briefly introduce what is the implicit bias and why we want to study the implicit bias to enhance our understanding about deep learning. So, so basically, the way to understand implicit bias is that we want to view the properties of the solution found by different algorithms. Because in deep learning, in the case that we have a very large model, and if we consider training loss function, we will have multiple candidate solutions. And in many cases, if you run different training algorithms, you may find different solutions. And in most cases, you will get different performance. So the goal to distinguish the benefit of different training algorithm and is to understand, okay, which solution will be found by these different algorithms and why they can give you different generalization performance. Okay, and all of this is just covered by the implicit bias result. Okay, so as I mentioned before, if we have the initial and the implicit bias result, we can further understand the tendency of different optimization algorithms for some particular problem. And then we can also study, okay, if we use we use different model architecture, and if we just slightly modify the model architecture a bit, like just add some shortcut, and what can we get, and whether we can really find different solutions give you different generalization. And then finally, the ultimate goal is just if we have a very precise implicit bias that is written as a function of the optimization algorithms and also the function of the model architecture, we can give a precise understanding about the performance gap between the different methods. So this is just some case, given the same data point and possible, if we use different model, if we use different optimization algorithms, we can perhaps find a different boundary. Okay, the implicit bias result is just some a detailed property of the solutions found by the algorithms or the architecture. And finally, it can be seen that okay, definitely these two solutions are pretty different. It can both give you zero training error, but they can perform very differently in terms of generalization. So we just want to study, okay, which algorithm is preferred by which which solution is preferred by which algorithm or which model architecture, so that we can further anticipate what we can get in the generalization performance. Okay, so yeah. So the next question is that, okay, we know that studying implicit bias is very important, which can give us better understanding about the relationship between the algorithm and model architecture and the model performance. So here, okay, how to study it? So ultimately, people just really want to understand what happens in many practical neural networks like transformer or just a very deep layer CNN model or just diffusion model, backbone model like UNet. Okay, but the question we first want to ask is, can we directly study the following models? Okay, so everybody can have a guess. So if we can really study these models, like there's already have many papers try to give you some very good like a theoretical result. But the answer is no. We hope so. But because of these models are too complicated, they're like in many cases we can only like formulate this model using Python code. Like in mathematics, we can even never have like a very nice formula for the practical models used like a transformer or very deep CNN models. But so in theory, they are technically intractable because we can even not like fully write the equations about the forward process. And then think about the backward process is even more complicated. Okay, so then, okay, what can we do? The first option is, okay, we are lazy. We just wait for some genius developing a fundamentally new and easy to follow techniques. So this, okay, but this is also very difficult. And sometimes we may not find such a like a very nice theory even in 50 years. And the second option is that, okay, if we really want to get some useful understanding about the models we use in practice, we can just start from the conventional model as to see, okay, whether we can have some simplification for the empirical models, and then we can find something in the conventional model that can be adapted to the complicated models. And then we can also still have something interesting to do. So we will just start from the conventional models, but we can use some modern algorithms and then model and modern architecture modules and see what happens. So this is the second option. That is also the motivation of our work. So, okay, as we have mentioned, we start from the conventional setting. So in terms of the implicit bias, a widely studied setting, or just we call it a standard setting, is a linear model on separable data. So the separable means that, okay, given the trend data points, we have like, they are linear separable, which means that we can find a linear classifier that can achieve zero training error on this like a bunch of data points. And also like, because of we have linear models and they have like the boundary, they have linear boundary, we can just slightly like rotate the linear boundary, we can still get like a zero training error. So this means that there are multiple classifiers that can give you zero training error. So, and this does also give us like a possible class of candidates we can study work on to see, okay, which candidate will be found by the algorithm. So this is just the goal of studying implicit bias in this standard setting. So a standard result is that if we consider logistical laws, which is exponential laws on these like linear models, and the widely known result is that if we consider gradient descent or stochastic gradient descent or just gradient descent with momentum, we can finally find the max L2 norm solution. So here, the max L2 norm solution is that, okay, we have a boundary, and then we can define margin, which is the smallest L2 norms between the data to the margin. And then we just find the max margin solution means that, okay, we can maximize the smallest margin over the data points. And then this result is made for the gradient descent or something like that. So here the base formula of the gradient descent said in each step we just first calculate the gradient at the current point, and then we just use this gradient to make updates using some like learning rate. And one key observation is that, okay, if we just use a gradient and for the linear models, the gradient is always the linear combination of the data points. And then if we consider running the algorithms for many steps, and if we consider like starting from the zero initialization, we can further to show that, okay, if we take t goes to infinity, and then the solution is also a linear combination of the data. So this is a very key important observation. So, yeah. And then
Hello, hello, hello. Can anyone hear me? I cannot hear Difan's
that,
sound.
okay, sorry?
Oh, I just lost your sound, but it comes back. Okay.
Okay. So
Okay.
then max margin solution is defined in this way. We want to minimize L2 norm, but we also want to guarantee that the margin for all the data is greater than 1. So actually another observation is that if we really try to stick for the KKT point of this solution, the theta star will also be the linear combination of the data. So this means that if your solution is not a linear combination of the data point, it will never be the L2 norm solution. Yes, this is a very key important observation that I will like I will discuss in the later like slides. So another thing is that for the gradient descent, we can also derive the so-called margin convergence rate. We want to show that, okay, the direction, which is also called the direction convergence, we categorize the cosine similarity between the solution found by the algorithm and the optimal one. And we show that, okay, this margin convergence will be like approximately 1 over log t, or just some like a small thing, slow decaying term, slow increasing term divided by log t, which is very slow. Like if you want to like achieve like some rate of margin convergence, you may need like exponentially more iterations. Okay, so now it's the well-known result, the baseline algorithm. You can see that is the baseline result, and then we just want to consider some modern architecture and modern algorithms that are widely used in deep learning. So about the architecture, we just consider the normalization layer, and we will just try to study, okay, what can normalization layer brings to us in terms of the implicit bias. And also we want to study the Adam algorithm, which is the most popular optimizer that has been like the default choice in many deep learning tasks. And in terms of implicit bias and other theoretical fields, these two things are not well understood. And then we just, okay, we just want to start from the previously discussed simple linear setting. We just want to add some new like contents to the like standard linear setting and see what happens, whether we can have a different implicit bias and whether we can have some benefit. So the first work is the implicit bias induced by the batch normalization. So here is just a basic introduction to the batch normalization. So the batch normalization is that, okay, if we have a bunch of data, and then for each data, we will have the activation output. And then we just want to make sure that given like a batch of the data point, their output should have like a zero mean and a unit variance. So how to do that is that we just, okay, give a batch of data. We first calculate the mean and the variance, and we just standardize it to have like a zero mean and a unit variance, which is very simple. And then after doing the normalization, we will have the scale and the shift. But in practice, we just consider the simple case, we only have the shift scale rather than, and we do not consider the shift. And also by adding the batch normalization to the linear model, we will obtain like this formula. So like we just divided by the mean, sorry, we just minus the mean and divided by the variance. So to make the model output to have like a zero mean and a unit variance. And then further, we just add like a gamma as a scaling parameter. So in the training process, we will train both like the linear weight W and the scale parameter gamma. And okay, and for simplicity, we just assume that the input data itself is already like standardized. Okay, and then we assume the input data has zero mean. So after putting x bar to be zero into the like this formula, we can get a simplified version of the batch normalization activation function, which is here. Like we just first calculate the inner product between W and X and divide it by the like sigma norm of W. And here the sigma is defined as the covariance matrix of the data. Okay, so now we just compare to the standard linear model, we just do two things. The first thing we do the normalization using the sigma norm of W. And the second thing is that we add some gamma as a scaling parameter that will be trained together with W. So here, yeah, then we consider gradient descent. So we also have the loss function. The loss function is also very straightforward. We just use in logistic loss. And the following is the formula of the gradient descent on both W and gamma. We can get some formula. Yeah. So here we can just do some analysis on the gradient of W and gamma. So one thing, is there something we can observe from the gradient calculations? So in terms of the gamma, and we can see some interesting thing. The first thing is that, okay, the update is always W is always orthogonal to the current iterate. But we can also show that, okay, all these vectors is still in the data space, like it's still the linear combination of the data points. And also, if we can also show that if the prediction is correct, and then we can observe that the gamma always get like a positive update. So which means that if the training error is zero, and then gamma will finally go to infinity in some sense. So, and this can also give you like a asymptotic result. And now we know that, as we have mentioned, the update of W is always in the data space, the linear span of the data points. So that will satisfy, and remember also the L2 max margin solution is also in the space spanned by the data points. So, and we can ask, okay, will the direction be different from the L2 max margin solution? But because they are both in this space spanned by the data points. So it is also likely that after adding the batch normalization, it will still converge the L2 max margin solution. Okay, so to answer that question, we can do just some like very simple experiments. We can see the overparameter setting where the number of data points is smaller than the dimension, and we just run some like very simple synthetic data. Okay, and after doing the optimization, and we find out something surprising, which is that for all the data points, their output is almost the same. All for all the data points, the inner product between W and Xi, they have the same length. So this is actually different from the minimum L2 margin. So that solution says that, okay, there are some bad points, and we just want to maximize that bad point, the margin of that bad points, but we do not push that all the data have the same margin. But in terms of the batch normalization, in our simple experiments, we find out that all the margin of the data becomes the same. So this means that, okay, in this case, perhaps we find a different solution compared to L2 margin solution. And also we find out that all the margin becomes the same. So we call that this is the uniform, it may converge to the uniform margin solution. Okay, so then we just want to see whether uniform solution is really the point that give you zero gradient. If it can give you zero gradient, yeah, it could be the one stationary point that will converge by the gradient descent. So this is just some simple calculation. This is gradient, and if we have the solution that has the uniform margin, which means that for all the data points, the inner product is always the same for for a certain value gamma. And after doing some calculation, we find out that okay, this part can definitely be zero, which means that uniform margin solution indeed leads to zero gradient. That is just a one stationary point of this new loss function, so which is definitely can be converged. That's invalid that gradient descent can converge to this point. So this is just our conjecture, and then we just want to prove it and see, okay, what is convergence rate? What is the margin convergence rate? And in order to prove it, we have some assumptions. The first thing is that if we really want to converge to the uniform margin solution, we first need to ensure that there exists the uniform margin solution. So here, the first assumption is that we assume the equation system has at least one solution. So this can be verified if we have the overparameter setting, like the dimension is greater than the number of trained data points. So in that case, we can definitely to prove that this assumption will hold, certainly. And there are some also definitions which just including the smallest eigenvalue of the data matrix, and also more importantly, which is the margin discrepancy. So here we just because we want to show the convergence of the to the uniform margin. So margin discrepancy just implies the margin uniformity. So if we have smaller d of w, and then we can say that the margin at a different data point, they are more aligned, they are more uniform. So this is just our main theory. We can prove two types of convergence. So the first one is in terms of the training loss convergence, and the second one is in terms of the margin convergence, or just similarly the direction convergence. So very standard result in the convex optimization or just optimization for the logistic regression, we can show that okay, the training loss function convergence rate is always like a 1/t, which is the same as before. And the good thing is that we can characterize the margin discrepancy convergence rate, which is the exponential to the a power of minus a log square of t, which is very fast, which is very rapid compared to the margin convergence rate for gradient descent, which is 1 over log of t. So this means that if we have the batch normalization, we can converge to the uniform solution, uniform margin solution with a much faster convergence rate, like direction convergence rate, compared to the gradient descent, which is just one advantage of batch normalization. So in practice, people can also observe that if you use batch normalization, you can achieve a faster convergence rate in terms of the generalization error, not even the training loss. The training loss convergence rate is always the same. And we can also do some extension to the very simple convolutional neural network. But the difference thing is that here we not only define the uniform margin for the different data, we define the uniform margin for all the patches of all the data points. So which means that we not only require the margin for all the data points they are same, but we also require that the margin for all the patches from all the data points they are uniform. So which means that okay, if for one particular patch the signal along that patch is not that strong, but the final like contribution to the margin they are the same. So which means that the weak signal in some patches will be amplified by the uniform margin results. So this can give some benefit if some signal is really weak in some particular patch that can still be discovered by the batch normalization. So this is just some empirical results in terms of the margin discrepancy. So like the left figure is something we have shown before. Like if we consider batch normalization, like finally all the data they will have the same margin. Then the right-hand side is we consider linear model without the batch normalization. In that case, like the data will have different margin. So this is just some empirical result on the synthetic data to highlight the difference between the training of with the batch normalization and the training without the batch normalization, which also like justify our theorem. And also we can see that okay, the margin convergence is pretty quick for the the model with batch normalization, and if we do not have batch normalization, like it is still like converging, like after many number of epochs. And we can also show that do some validation for the CNN model. So here just some variance. Like the uniformity is just some variance calculation, and the smaller variance means that like better uniformity. And here we can also show that we consider the training for a binary classification using draw from the CIVA10 model, the CIVA10 dataset. So and we characterize the margin uniformity for different the class of data. So for dog, like definitely the blue line is strictly smaller than the orange line, and this is also the case for cat, which means that okay, if we consider single model, the solution for if we consider representation outputted by the single model, if we have the batch normalization, it will always become like a more uniform compared to the model without batch normalization. Okay, so yeah, so this is just the first part of my talk. So far, sorry, I still have like some proof sketch. Just okay. So the proof sketch is pretty like straightforward, and we just want to prove that okay, we can converge to the uniform margin solution. So the idea is pretty straightforward. We just characterize like the inner product in the update direction and the ground and the point we want to converge. So if this one is positive, which means that okay, we can always towards to this like a uniform margin solution W star. So and by doing some simple calculation, we find out something like a good. So first thing is that we find out that okay, these two products will have the same sign. So and if after the multiplication, we will always have something positive. So which means that okay, no matter which W you are located at, and if you consider gradient direction, they will always be positively correlated with W star, which means that the correlation between W star will always be like larger. So, and also the right-hand side is something related to margin discrepancy quantity, so which will be very good for us to have some like a sharp characterization on the margin discrepancy. And also by combining that, we can prove some like a lower bound in terms of the increasing between the inner product between W and the W star. So this one is always increasing and governed by the margin discrepancy. And also we can because we want to prove the margin direction, so we want to like remove the setting that this increasing of inner product is caused by the increasing of the norm of WT. So here just we can show that okay, this inner product increases like O eta per iteration, while the norm of W star only norm of WT only increases O is squared per iteration, which means that if we use very small learning rate, the increasing of the norm is negligible compared to the increasing of the inner product. Okay, and the increasing of the norm, slow increasing of the norm is is because of the gradient is always orthogonal to the data points, or orthogonal to the WT. So that will lead to like a slow increasing of the norm of WT. So by combining this, we can show that okay, and the direction of WT will always be more close to W star after many number of iterations. So this can give like our final result, final convergence rate in terms of the loss function and the direction. So this is just the first part of my talk. So far, any questions so far?
So let me ask a very simple question. What is the difference between this mixed margin and uniform margin? Which is good, better for the classification? It seems to me mixed margins should be much better. Or
Oh, so
I don't know.
this has like depends on the data distribution. This depends on different tasks. So just consider one case. So if you have like the label noise, like the some data they have different run labels, and if you still do the max margin, and you will have some overfitting on that like run labels. But you have the uniform margin, you will just pay like you will not emphasize a lot on the data with small margin. So because we just push every data have uniform margin, so the overfitting could be uh could be mitigated. So in that case, like I think uniform margin could be better. But if the data is very clean and you just want to learn something that has max margin, that is to give you like a more robust data model. So in that case, I think like max margin could be a better choice. So it really depends on which kind of data model you are using.
Okay, thank you.
Okay, so thanks for the question. So I guess we can move on to the second part of my talk. So the first part we just discussed the role of different model architecture and see okay whether we can get and really whether we really get some different implicit space result and whether we can have some benefit. And the one benefit we have shown is that if we have batch normalization, we can get a faster convergence in terms of the direction. And the second part is that we still can consider linear model, but we consider using a different optimization algorithm. So here we consider Adam, which is I guess everybody know what is Adam, and everybody have heard of that Adam is used like in many deep learning tasks. And if you do not specify some if you do not specific using some other optimizer in training neural networks, the Adam is always the default choice. So, but here I will first to do some recap of the formula for Adam. I guess in many cases people just try to using one live code to code Adam, but no, I guess many people do not know the exact update formula of Adam. So here the Adam is just they have like two terms to be updated. The first one is the momentum. The second, which is m of t. The second one is the second order momentum, which is denoted by v of t. So M is just an accumulation of the historical gradient, and V is just accumulation of the historical gradient square. And here the square is just something like calculated in a coordinate wise, like we just consider a square for all the coordinates of the day of the gradient and then take a like exponential average. So after getting the momentum and the second order momentum, we're just using the second order momentum to normalize the first order momentum to get the update. And here, in many cases, people also will add some like small quantity called epsilon in the denominator to avoid some instability calculation. So yeah, and here the beta 1, beta 2 just some like parameter people will try to use in practice. So in our theorem, we just assume that the beta 1 and beta 2 they are constant. So in practice, people will use that like the point 9 for beta 1 or point 95 or just point 99 for beta 2. Okay, so like before moving on to the final theorem, we can also get some observations about Adam to see okay what can we anticipate, what we would like to get if we run Adam for the linear regression for the linear classification problem. So the first is that the updated Adam is not on the span of data point. So this is just because we use square root of VT to normalize MT. So this normalization is taken in the coordinates manner. So which means that it is not just it will break the linear combination of the data points. Even the gradient itself is still the linear combination of the data, but after this normalization, the updated direction will no longer be the linear combination of the data, especially in the overparameter setting. So in this case, the implicit bias may no longer be the L2 max margin solution because that solution must be the span of the data point, linear span of data points. And the second observation is that if we consider very small step size, and then the momentum will no longer be that like dominating term because like if you consider small learning rate and the weight will not change a lot during a very long training period. So in that case, in this longer training period, all the data gradient will always be similar. So in that case, so momentum will be very similar to the current gradient, and the second order momentum will be very similar to the current gradient square. And then by calculating this like normalization calculation, and we find out that mk divided by like vk is approximately the sine of the gradient. So this means that in the late training stage, where the like gradient is small and the learning rate is small, and then Adam will behave like a sine of the gradient descent. We first calculate the gradient and then take a sine and use the sine to make the model update. And then this is the sine gradient descent is also like very just kind of L infinity normalize the gradient. So this is just a basic two observation, and then we just see okay what happens. So first thing is that we just can do some like a very simple case to show that the sine gradient descent will have different margin, different like implicit bias compared to the L2 max margin solution. So first is that the sine of the gradient descent will tends to balance the quantity of each coordinates, because if you only consider two data points and if you consider sine of gradient descent, so each update the update along different directions, along different coordinates will also be the same. They will always be the same. So finally, in this simple case, the final convergent direction will be 1, 1. Well, if we consider L2 max margin solution, that will have a different margin. So in this case, we can already identify that, okay, that atom will never converge to the L2 max margin solution. Well, the sine gradient descent will have like likely to keep in small L infinity norm, because they will just to want to make all the coordinates to have the same value. So finally, try to like reduce L infinity norm. So here we just have a conjecture about the implicit bias of atom. Like it may want to reduce L infinity norm of the weights, but also want to make the training loss become small to make the training error to be 0. So in like just like the standard L2 max margin solution, we just have a conjecture that atom is perhaps like converging to the L infinity max margin solution. So here we then have some assumptions when we just consider the learning rate decaying, like the when t goes to infinity, the learning rate is approaching 0. And also we consider the summation of the learning rate is going to the infinity to ensure that, okay, we can run the algorithms for like an infinite like a length. And then like why we need to assume the step size goes to like a 0? This is because if learning rate is large and we cannot guarantee that atom is very close to the sign of gradient descent, as I have just mentioned before. So at least we need the learning rate to be finally converging to 0, so that we can apply some analysis of the sign of a gradient descent to make our proof like be accomplished. And the second assumption is just some assumption about initialization. This is because we have some normalization in the denominator. So if the initialization, if for some bad initialization, the denominator is very small, we will have some instability. So that is not something we want to happen. And this is just some basic implicit bias theoretical result of our work. So we first have the formal definition of the infinity max margin. We just want to maximize the margin. So the margin is just okay, the minimum of the inner product like over all the data points, and we just want to maximize this margin while under the constraint that L infinity norm of W is smaller than 1. Okay, so so this is just a definition of the L infinity max margin, and then in order to prove the direction convergence, we can like equivalent to prove the margin convergence. Like we just want to first characterize the L infinity margin of the solution found by the gradient descent by the atom. Okay, on the different loss function, we consider logistic loss and exponential loss, and then we can prove that the margin achieved by the atom at different iterations will become like closer to the max margin after a number of iterations. So this is actually some complicated like formula, and I will try to simplify it later. So like the general theory is that if we consider the standard like any linear scheduling, and for the logistic loss and for the exponential loss, we can prove the margin convergence, and atom can definitely find the infinity max margin solution. And later we just really want to do some simplification about the bound on the right-hand side because it is just a function of all the learning rate at different iterations. So here we just consider some specific like learning rate, some specific learning rate scheduling. We consider the learning rate decay, and which is a polynomial decay like in the order of t to the power of minus alpha. And then, okay, we can show that if we have like a L, and for different region of A, we can get a different convergence rate in terms of the margin. So, and the good thing is that we can observe that, okay, if we consider like a relatively good, like learning rate scheduling, like if the learning rate is scheduling is slower than 1 over t, like when, which is the case of alpha equal to 1. And then we can always get a polynomial margin convergence rate or just the direction convergence rate. And also remember, for the gradient descent, if we do not use the atom, for the gradient descent, the margin convergence rate is 1 over log t. So in this case, we can also like confirm the advantage of atom in terms of the margin convergence rate, because for the atom, the convergence rate is polynomial, but for the gradient descent, the convergence rate is 1 over log t. And here just okay, so now we already get some results. So and then I would like to like briefly show some proof sketch. So the first thing I need to mention is that, as I have mentioned before, we have some like very good intuition. Atom will be very close to sign of gradient descent. But in terms of analysis, we need to like quantitatively to categorize the difference between atom and sign of gradient descent. So the first thing is that, okay, we can show that the first order momentum will finally converge to the gradient, and the difference is upper bounded by some like by some order first like big O of eta, like if big O of eta t. So which means that if the final phase, the learning rate is small, and then the difference is also small. And this is also true for the second order momentum, which we hope that the Vt will be very close to the square of the gradient. So this is also governed by the learning rate. Like if the learning rate square root of the learning rate is small, and we can also show that difference of the approximation of the second order momentum to the gradient square is also very small. So and by combining them together, when t is very large, and we have a beta 1, beta 2 to the power of t to be close to 0, and also when eta t goes to 0, and then we can confirm that the update of the atom become very similar to the sign of gradient. And then we can also derive some like convergence rate or just convergence result in terms of the training loss. Like we can show that, okay, the training loss is always decreasing if the training loss is small, and the decreasing is also small. So this is just some like a routine proof. And then if because based on the loss decreasing, and then we can prove some bound for the margin, which is derived this one. And then after doing the margin, we can also prove the bound on the infinity norm increasing. So this is kind of easy if we have known that the atom behaves similar to the sign of the gradient. So putting things together, because we want to study the margin convergence, so we just want to calculate the margin achieved by WT. So which is the inner product between divided by the infinity of WT. So just combining the previous two things together, we can have this kind of thing. So the good thing is that, okay, the dominating term and the denominator and numerator, they are pretty the same. So which means that finally, as long as the summation of eta t goes to infinity, okay, so the right-hand side will be always greater than gamma, and the remaining part is just the convergence rate to the maximum margin. So that we can calculate when we are using different learning rate scheduling. Okay, so now we can also have some empirical result to verify our theorem. So for the left-hand figure is just we categorize different algorithm when using with see how it behaves for like the L2 margin, L infinity margin. So finally, we can definitely show that after a number of iterations, the atom will converge to the maximum L infinity margin, while the gradient descent cannot do so, and the gradient descent with the momentum can also not achieve the converge to the max L infinity margin. While as a comparison, if we consider L2 margin, The gradient descent will finally converge to L2 margin, but you can see the rate is much slower, even after like 1 million iterations. It is still like a substantial gap between the L2 margin achieved by gradient descent and the max L2 margin. But for the atom, like the convergence rate can be much faster. So this also like backs up our theorem. And we also consider something like try to verify our result when using different learning scheduling. And we find out that, okay, if we consider the log plot, the final convergence rate is almost like a linear curve. So this means that this just also demonstrates the polynomial margin convergence, because only if you have the polynomial margin convergence in the log curve, it will behave like a linear straight lines. Okay, so this is just some summary of so before moving on to summary, do you have like any questions so far for the second part of my work? Okay, so let's move on to the summary and some future direction I would like to discuss. So about summary, so here we just in this talk we just discussed our recent works about the implicit bias when using different optimization algorithms and different architecture. So we just do some case studies, and we show that, okay, if we use different optimization algorithms, we will possibly have different bias, and also when using different architectures, we will also have different bias. And these different bias will have different solutions, and that can be kind of defined as the uniform margin or just L infinity max margin solution. And the good thing is that we also demonstrate that these empirical designs, like adding batch normalization layer or just using atom, can have a faster margin convergence rate. So that is the possibly one reason that why people try to use this thing in the training of deep neural networks, because people want to get like a faster convergence in order to save the computation like complexity. And we also want to discuss some future work. So like one about the normalization techniques is one future work is that, okay, we have many different normalization techniques. So the batch normalization is actually kind of out of date. That is works pretty well for the signal model. But now we are using transformer model. We are going to the larger language model area. So in that case, the layer normalization is a more popular choice in the modern like large scale transformer based models. And then uh, in that case, in theorem, in this paper, we can see the linear model and derive some benefit in terms of the batch normalization. But if we want to consider neural network models, even for the simplest two-layer neural networks, if we consider normalization layer, can we get some benefit? If we can, especially when we have like a layer normalization, that really requires you to have a neural network, because layer normalization is performed over the neurons. It cannot perform on the one single linear models. So in that case, what can we just extend our theoretical analysis to the neural network model is very interesting future direction. And also in practice, people do not use a full batch gradient descent, but people use stochastic gradient descent. So if you consider batch normalization, this will be different, because the batch normalization is calculated over a batch. But in terms of the layer normalization, I think this could still be good, because layer normalization does not depend on the input batch of the data. And finally, we can also consider if the model is extremely large scale, and it has been observed that by adding many normalization layers, we can make the training of large language model become more stable. So can we also prove that in a theorem to show that if we have the normalization layer, can we just show that the training is more stable? And also about the Adam algorithm, the benefit of the Adam has not been fully investigated. We only show that Adam has like a faster like margin convergence rate, and we also show that Adam can converge to the maximum L infinity margin, but we haven't demonstrated that in which cases the maximum L infinity margin is a better choice compared to the maximum L2 margin. And also here we also want to study, okay, what happens for non-convex models, because like I strongly believe that in many cases Adam can be better, especially when the model has non-convex modeling, because in that case, even in the nowadays in our work, atom has nothing different between the sign of gradient. But in practice, if you run some experiment, the atom will be much better compared to sign of gradient. So that we guess that is the role of the momentum part. And momentum part will have like a very strong effect in early training phase, especially for non-convex models. Okay, and also what happens if we consider stochastic gradient is that is very critical for atom-based research because for the atom, even for the sign of gradient descent, if you consider stochastic version, that will be very different from the full batch version. And also in large language model, we typically have like a weight decay, which is the atom W that we put the weight decay outside of the atom update. So what happens if we have the weight decay and why atom W is becoming a default choice in training large language model? Okay, and finally is that atom is just designed like in 10 years ago, but there are many papers try to improve atom from different perspective. So we also want to try to extend some research to that directions, like improving the stability, to improve the memory cost and efficiency, especially for large language model. Okay, so that is of my talk. And do you have any questions so far?
Thanks for your great talk. Do we have questions from audience? If you do, either you can type your question to the chat or unmute yourself. Either way is good. It's very theoretical work. Do we have any implication for our practical use? Like we have studied this implicit bias. So Professor Zhou, do you have any implication?
I think this is just also one thing I'm considering. So like the topic I discussed in this talk is it's basically following very conventional theoretical research, and it is more like explaining. It is more like explanation rather than developing something new. So I guess
Yeah.
directly applying the theoretical to the practical design is kind of difficult. But something we can but I think something I'm recently doing is just try to, as I have mentioned, like in large language model, we care a lot about training stability, and we find people have found out that like the normalization technique can certainly like mitigate the stability. So and one of my recent like exploration is that we just try to like simplify the training of a large language model to show whether there is some consistency between the like perhaps two-layer models and large language models. And we have already pinned down that the training stability mostly occur in the first layer of large language model. So in that case, I think we can extend our research to show like to find out like better stabilization techniques, like how to use the normalization layer, how to modify the normalization layer a bit to make the training curve become more stable, especially when we have like a kind of a large learning rate. So in that case, that is something I'm doing. I think that we can bridge, we can like we can connect the bridge between the theorem and the practice.
Okay. In the atom part, the implicit bias is L infinity margin. Is it related to the is it related to this descent is equivalent to coordinate descent? Like
That is very
L
good catch.
one?
That
Yeah.
entirely. I have to say it is because we do the like coordinate normalization and we push the update of all the coordinate to be very similar. So that is the major reason to the like infinity max margin solution.
Oh yeah. Yes.
And
Thanks.
also, if you consider other similar stuff like AdGrad or MSROP, that will give you similar thing because as long as you do the normalization in your coordinate wise, you can get a similar result. And there is also recent paper they trying to do the coordinate normalization in different ways. Like they can also try to step the descent, and they will have like the corresponding implicit bias. That paper is released like last month.
Okay. Thanks. So do you have questions? If no, let's thank Professor Zhou. And this video will be on YouTube soon. Okay. Thanks, Difan.
Okay. Thank you for like listening to my talk and bye bye.
Okay, bye bye. See you.
Okay.